Welcome to this first lecture on many electron systems and approaches to solving for many electron systems, which is going to lead up to a description of the basic theory behind density functional theory. This first lecture is an introduction and it builds on the previous lectures by Alex Schluger on the hydrogen atom. Once you go beyond one electron, we cannot analytically solve for the wave function. It becomes just impossibly complex, though very accurate calculations exist for up to about 4 electrons. So we're going to consider two non-interacting electrons, just to start with, and they're going to be in separate wave functions, which we'll write as phi a of x1, and we'll have phi b of x2. Now please notice that x is a composite coordinate. It's equivalent to a three-dimensional position and a spin, though often we won't actually be explicit about the spin. If this were the situation, then we could write the many-body wave function, which I'll write with a capital psi of x1 and x2 as a simple product, phi a of x1, phi b of x2. But of course, electrons are not distinguishable, so that would require distinguishable electrons. They are indistinguishable, and so they have to obey the Pauli exclusion principle, which says that no two electrons can share the same eigenstate or the same wave function. Given that, it means that the wave function overall must be antisymmetric. In other words, if you swap two particles, then the sign must change. A simple way to do this for the simple case of two electrons is to write it as follows. There's capital psi of x1 and x2. That's equal to some normalization constant into phi a of x1, phi b of x2, minus phi a of x2, phi b of x1. And you can see there that if x1 were to equal x2, in other words, if the two electrons were to be at the same point in space, we would get 0. In other words, the wave function would disappear. So it's not possible to have that. The general solution is most easily written in the following form. This is for many electrons. We would write capital psi for the many-body wave function of x1, x2 up to xn, where n is the number of electrons, is equal to, again, a normalization constant times the sum over all possible permutations p of minus 1 to the power of p, p hat, which is a permutation operator, and then we just write psi a of x1, phi, that should be a phi a, let me just correct that. We've got phi a of x1, phi b of x2, all the way up to phi n of xn. And notice that in this case, the operator p permutes, in other words, rearranges, and an even number of permutations would give us no sign change, whereas an odd number would give us a sign change, and therefore we will obey the anti-symmetrization. It's important to notice that p commutes with the Hamiltonian. So that's a simple statement of what's happening in terms of the many-body wave function. Notice that we're not really going to consider ways of solving for the many-body wave function. We're interested solely in density functional theory. There are other approaches which we'll talk about in other parts of the course. So now let's turn to the question of operators. In particular, we're interested in operators for kinetic and potential energy. Now we can write the kinetic energy operator in a very simple form. It's minus h bar squared over 2m, where m is the mass of the electron, h bar is the reduced Planck's constant. Sum from I is equal to 1 to capital N of del squared I, and note that del squared I operates only on xi, or actually rather Ri. Let's change that. So this is a very simple operator. You will often find that if we're using atomic units, we set h bar equal to 1 along with m and the charge on the electron. So in that case, we would have minus a half del squared I. And I will often use these units. So h bar is equal to m is equal to E is equal to 4 pi epsilon naught is equal to 1. It makes the formulae significantly simpler. The potential energy is all electrostatic, and in the systems we're interested in, that is atoms, molecules and materials, we have two sources of an electrostatic interaction, the nuclei and the electrons. If we write the potential energy for an electron at a position r in the nuclear electrostatic field as little v of r, so this is the potential energy, Pe, for an electron in the nuclear field, then we can write the total potential energy, which we'll write as a capital V with a hat over to indicate it's an operator. It's the sum, again, over I is equal to 1 to n of little v of Ri. Now, if we consider the bare nuclei, then we can just write the potentials in terms of the positions of the nuclei and the positions of the electrons in a simple, obvious way. Frequently in condensed matter, we will use an approach called pseudopotentials, and that is something which we will cover in a later lecture. The interactions between electrons is a simple electrostatic. So if we have electrons at two positions, at R1 and R2, then the interaction is just a simple 1 over 4 pi epsilon naught magnitude of R1 minus R2, which in atomic units is just simply 1 over the magnitude of R1 minus R2, which I find simpler to write. And therefore, the total electrostatic energy from the nuclei can be written as a half, and that's to avoid double counting, times the sum over I not equal to j of E squared over 4 pi epsilon naught Ri minus Rj, or if you preferred, you could write that as a sum over I less than j. So notice that avoids both the double counting and the having two electrons not interacting with each other, times 1 over Ri minus Rj, and notice that here again I've used atomic units in the second set. So the total Hamiltonian is then given by the sum of all of those terms. So we can write H is equal to T plus U plus V, which just defines the problem. It's very simple to write down and almost entirely impossible to solve for. And we would then write the Schrödinger equation, the time-independent Schrödinger equation, as H acting on capital psi of x1, x2, up to xn is equal to an energy E. Let's actually put a subscript on the psi and on the E, En, psi n, like this. Now, at this point, you should ensure that you are happy with some of the other concepts covered in the notes, namely the ideas of expectation values of operators. These are standard quantum mechanical ideas, and the orthogonality of eigenstates. Those are covered in the detailed notes. And we're also going to use the variational principle, which again is detailed in the notes, which enables us to say that the expectation value of H in a state psi, so I'm going to write this as I go, is always going to be greater than or equal to the energy of the ground state, where E0 is the ground state energy. This is a very helpful principle. It enables us, for instance, to create a trial wave function, psi t is a trial wave function with some parameters, and we can then vary those parameters to find the lowest energy, and we guarantee that that will approach the ground state from above. That's the end of this introductory material. Please ensure that you've read the accompanying notes and that you understand them, and bring along any questions to the session that we have